kind of. You can go running. No, walking, sorry. Okay, so let's start today. Professor Dr. Ippolito is going to give us a talk for this. And today, the second session will be oral session. We are not going to have this one, okay? Thank you.
Well, good morning for everyone. And first of all, we should thank Pedro and Alexander for the invitation for this seminar, workshop, and to present this talk. And I will give an overview of some possible applications of fiber optic sensors in biomechanics. And that's more or less the summary of what I intend to talk. First, a situation where we are, not geographically speaking, but in the market, and some historical remarks about that and the birth of biomechanic sensors, fiber optic biomechanic sensors, and then most of the talk I will show you some applications of such sensors. So that's the starting, the beginning of the talk. What's that? Let's say global healthcare estimates are about $10 trillion per year. These are data from 22 that were published by the World Health Organization, 23. And this corresponds more or less to 10% of the global economic output of all our economies together. But we have a large asymmetry in the process because 80% of this figure goes to high-income countries where we have only less than 16% of the global population. So this is, and you can see this in this graph. This is a relative percentage of the expenditures, and the yellow bars represent the high-income countries. Even if we count the upper middle income countries, like Brazil is struggling to keep the position there, it's still these two segments, the population receives 90% of all the amount, and of course this implies that lower income countries, they lack care for the population, in fact, because they cannot afford equipment, supplies, and services that are needed for that. And in fact, you can see that the low-income countries, they didn't show here. If you pick the original paper, was in Optimum Photonic News in April, you can see that in the last years, you can see a small headline here, but it's really very small. So that is not. So this is the situation of the biomedical market, and eventually, I believe people that work on optical sensing technology and so on, we believe that optics and photonics can create more affordable, portable patient care device to close this gap, particularly in point of care, but it's difficult to enter to the point of care segment. And this is if you look to the patient care, we have about 20% of that figures, about 2 trillion, are medical device for clinical use. Capital, equipment, and so on is about half a trillion, and 20% of that amount is based on optics and photonics nowadays. We have examples in radiology for imaging, laser surgery and other applications, optical coherence tomography, photodynamics therapy, particularly in cancer, flow cytometry, hair, wrinkle, and tattoo removal. So that's tattoo removal now as a percentage of the global economy. Optical metrology, of course, imaging techniques, and so on. And there is also a share that is in consumables. And particularly, we have also a market for photosensitive reagents that are used for DNA sequencing and drug research, detection of virus, and so on. I believe that yesterday Professor Andrea showed this test with a strip chromatography device that is a photosensitive agent that's used there. And also for catheter coronary stents, because they are manufactured by laser tools and also contact lenses and etc. Well, but one of the main problems that we encounter is that the new devices, they are usually subject to regulatory approval. They are processes that are expensive and not even assured for all the segments. And what about the market for research, where most of us are in the moment? We have a good community of optical and photonics addressing medical science and new tools development, what's called the second biomedical market by the authors. Basically, university, research hospitals, and research institutes linked to science, to health sciences. And we have a science push that came from in vitro experiments, for instance, using images of mice, one of the animals that were used in laboratories, or even going to in vitro human samples and patients for tests of a procedure for the AG. Most of the tools in this market, they are originally not destined to the patient care. They are usually research tools that are used in labs for the purpose of advancing science and tools. And even in this case, we have a good amount of money. For instance, the National Institute of Health in the US gives approximately 50 billion per year, most to university and research hospitals. This is much smaller than the patient care amount, but it still is a very sizable segment of the market. And this usually is used in labor, personal and so on, new equipment and supplies for our research. So we have to decide in which market are we, not you, but we in. You see, many of optical photonics companies, optics is a very particular branch of physics. It requires skilled personnel in several activities. It still is handmade. So you need normally these companies, they are fitted for a low volume, high performance products, to research labs. Even we buy, let's say, a gas chromatography or something that uses optics inside, alignment of the optical components and cleaning, processing, calibration, and so on. This requires a high demand of technical expertise. On the other hand, big companies are usually selling or serving the patient care sector because they have resources first to invest in the production and the product, to ask and eventually win the regulatory approval, and they can spread financial risk on several products to see if one of them is successful, it will compensate for the spread of money. And so that the spin-off companies that usually came out from our companies, from our universities, They are important engines for innovation. And then partnership with big companies can bring the new solutions to the market. It's very difficult for one of these companies to access directly the market with their products. Yeah? So the important opportunity for opticals in photonics is to help expand affordable healthcare to underserved communities. And if you work on that, one good advice is do your research by walking around. Go to the, let's say, the healthcare units close to your place to see what are the difficulties they have and see what can you eventually locate an application that you can take out from your lab, to the day-to-day problems faced in the frontline healthcare. And so this is okay, now I can go to my talk about the technical aspects of fiber optic sensors. First of all, I don't know, most of you probably have had some contact with them, but a fiber optic sensor usually has a channel for light input, a channel for light output that usually is optical fibers or waveguides in case, and then you have some process to modulate the light that's carried to these channels. And this can be done by physical agents like strain or temperature, and can be chemical agents like pH, or it can even be a biomedical aspect like antigen antibody binding in some films and materials. So that this is usually the aspect, and obviously there is you need some processing unit in which you will have an optical source and then some auxiliary elements that goes to the probe, came back, and are detected and are processed by electronic usual procedures for signal conditioning and processing. Okay, and then let's go a little about history, and I will only talk about history in Brazil. For the present generations is an old field of history, and about 40 years of research in optical fiber sensors in Brazil. In fact, the first work that is related to sensing with fiber optics was thermal sensing with liquid core fibers. That was done in 1984. And in fact, it was just 1 year after the first international conference on optical fiber sensors that was held in London, 1983. And in that conference, the first paper published in the conference about biosensing with fiber optic sensors was a fiber optic thermometer, in which there is a core of fiber, and then a small enclosure with a proper liquid, and then there is reflection on the tip of on the exposed part of the core, and then the light incoming comes back, and as temperature changes and you change the absorption or the refractive index of the liquid, the light output reflected is different. Just basic Fresnel law of reflection. And this is very interesting because Susanna was not working with fiber optic sensors. She was working with a different structure in which the fiber core was a liquid. She has, in fact, a glass tube, a fiber glass in the form of a tube, with a hollow core, what they call today a hollow core fiber, filled with liquid. And then she saw that the changes in the refractive index of the core, of course, also affect the propagation of light, and that was turned to be a sensor for temperature. Okay. Then we have along the 80s and 90s several groups in Brazil that were working with different kinds of optical fiber sensors, most of them in Southeast region, Rio de Janeiro, São Paulo. There were some examples in Northeast, in Pernambuco, and most for physical parameters. There was this work by the group of Federal University of Rio de Janeiro that was a pressure sensor for biomedical use, a little later. And when I moved to Curitiba at the start of the 90s, we also developed a thermometer for microwave hyperthermia processes. But these are related to general fiber optics in our history. Okay. I will talk most on this talk. I will talk most on the. Is the sound okay? Are you listening? Okay. I have some different feedback. I will talk most about the sensors that are based on fiber black gratings. Alexander talked very widely yesterday about this device. The black gratings and the long period gratings that he showed, also some graphs, are periodic modulations of the refractive index of the fiber along the propagation axis, the axis of the fiber. And we usually represent by some crossed bars in the line of the fiber. This is a periodic structure, like the long period gratings also are periodic structure, and all periodic structures show some rejection band. So if we choose the parameters of the grating, in this case, usually we choose the spacing, the pitch between two successive high, low changes of refractive index, we can obtain a block in the propagation for a specific frequency or wavelength, so that if we have some broadband source sending light through the fiber, this band cannot propagate, the rest will pass, but this band is reflected back, and if you use some device to separate incoming and outgoing light, then we can analyze and you can see a reflection spectrum. Long period gratings like the one shown by Alexander usually only show the transmission band, because the other one is coupled to the foreign medium. And such bands are sensitive either, for instance, physical or even chemical parameters through the evanescent field. But let's say directly we can change in strain or temperature or some other more complex parameter can shift the frequency of the band. So they are attractive for sensing, and they are attractive in principle to biomedical and biological sensing. That's first because of the small dimensions and the reduced mass. We have about 1 millimeter of fiber black grating in a fiber optics that has 125 micron diameter, so that the mass is in the micrograms or hundreds of micrograms, in fact. They are usually done in silica fibers that are chemically inert for most of the range of chemical products. As a dielectric, they have immunity to electromagnetic interference. That's quite useful in some environments. And silicas has some biocompatibility that you can use it in some applications. So that there have been a lot of work on fiber sensors based on black gratings in biomedicine, biology, and so on. And let's say the start of the applications of such sensors in biomechanics, like we call it now, it was on the turn of the century some papers that were presented in conference in 2000 and published in 2001. One of them by Chin co-workers, it was a dental splint that he used by the time to monitor. They are used in orthodontics, but they were used to monitor the pressure and the temperature in the mouth. In fact, here that's the evolution of the temperature where the sensor was put in the mouth of a patient, and this one are the measured strains, let's say deformation caused by the pressure of the teeth on the device. And these are, in fact, were done with in living agent in a patient. And our group in Curitiba also published a different application. It was a respiratory monitor. It was an elastic strap with a fiber sensor in the middle that was used to detect by the expansion of the thorax the respiratory frequency, and this one is used. The second, the shaded region here, is a burst of a device to trigger an electrically assisted ventilation device. The intention of this apparatus is to using that bursts to electrodes that are placed in the chest of the patient to induce inspiration. And this is used to, let's say, regularize the situation of respiratory arrest caused either by accidents or some kind of open thorax surgery, and to help the patient to resume the normal process. And this was the original destination of the sensor. You can see that here we have some spectra of respiration in rest conditions, and here in a situation that's more close to respiratory arrest, because respiratory arrest usually is partial, occurs in one of the lungs. And so that the organism, in order to compensate for the reduced volume of respiration, it has to increase the frequency. So it is you have a more frequent repetition of the admittance of air, and this is the high frequency, but also this causes a limitation in volume. So that to simulate this condition in lab, we simply limited the volume that the person could take in each cycle of the respiration. So this is partial respiratory arrest, and you can see that the wow, that was very fast. I don't. Wow. I don't know what happened, but it was. You can see that the change in the frequency spectrum of these two situations. Well, and this was very nice in the lab. We have a prototype working. We have it was work jointly with a group of biomedical engineering of the Catholic University in Curitiba, so that they have the electronic part of the device to test and so on. But we didn't have a product to sell to the market. Maybe someone will sell it. But there were other developments that are in the market now. Not by Brazilian companies, but foreign companies that applied the idea. They started with embedding the fibers in textiles to obtain some kind of jacket they can put. And initially they were intended to monitor the respiration process of patients that need attention, old persons, so on. But In fact, they obtained a better market for the product and the rescuers in action. I say paramedics, firemen, situations of earthquakes where a lot of people are working to remove the debris and look for persons, so on, so that those teams, they suffer from stress, from laboral stress in case. And let's say the big market now for the product is just the jackets to monitor the rescuers to see if someone needs to be replaced or take some rest and so on. Not good. And another application that came to the market just in the year before the COVID-19 pandemics from a Polish company, supported by the European Union Research Council. They offer the monitoring of stress conditions in magnetic resonance imaging apparatus during the scanning. Most of people, I believe, or part of people, they are afraid of MRI scanning because you have to enter something that's like a tube, small, not so big, and it's very noisy, in fact, even with hair plugs. It's very noisy, so that usually the physicians that are working there, paramedics, they give you a trigger to stop the process you are feeling bad. Yeah? And this is this device is some kind of tapestry that goes in the bed behind the patient that is laid over, and the FFG sensors there are monitoring both the respiratory frequency, but it's possible also to detect secondary frequencies. I have not shown in our paper. We also have done that. We can detect other frequencies, for instance, the cardiac rhythms of the heart, so that they can look to those frequencies to see some sign of stress in the patient, and they can stop the process, even if the patient is so afraid that it's freezed, cannot use the trigger. So it is an interesting application. Okay, and of course, in terms of the lab, we also use it to see response along walk or run, putting some sensors in along muscles in some patients that were our graduate students. Yeah, and they developed several walking, running process. You can see changes in the response of the sensor for different times in different conditions, and you can see different spectra related to I believe this is an intense walk, and this is like a Pilates apparatus up and down in steps, so that there are different response. Okay, this is for people, but it's possible also to have biomechanical sensors in animals, in cattle, for instance. This has been done by a surgery that attached a sensor. There is a small plug where the sensor is mounted, in the jaw of the cattle, and then it could be monitored after recovery during ingestion of aliments, and we have some different responses depending of the type of aliment. You see here is a supplementary some kind of ration, but this is hay, that's common. This is some kind of high grass, also dried seed leaves, and this is the rumination process of the cattle after that, and this is the idle condition when there is no ingestion of food, no processing of food. And the better details show the response for here for three processes: ration, hay, and rumination. and we can also have the strain distribution in the sensor along the time during the showing and so on. So it can give some information for the people of animal science veterinary aspects, and even for producers, people that were farmers with cattle that can, let's say, direct the ingestion of aliments to the animals. Okay, from that one, we also show that it's possible to use such kind of sensors more close to a medical or clinical procedure in the case of fracture healing. Initially, it was done by strain modeling. This is right. In this case, we have some prostheses. There are femur prostheses. Is design, and here is a finite element mesh of the process, and we can analyze, for instance, the strain at different positions of the processes when a load is applied in the process in the bone. And this also were used in this case to correlate the numerical modeling of strain by finite element methods to measure the experimental strain, so that you have a good agreement of the data. And this was is important in order that, say, one of the goals of such a study that has been achieved by, at least for what I know, in some clinical hospitals in Italy, is to design the prosthesis to the patient, so that when there is need of a prosthesis, you can make a densitometry to see the bone characteristics of the patient, and then you can use the data with the simulation to design the prosthesis to be coupled. There is quite different from the classical approach in femur surgery, for instance, that you have several, let's say, preset processes depending on the dimensions of the bone. You will use A, B, C, D, or E, but they are not specifically fit to your body. And this is, can cause pain, or let's say walking is not so perfect for patients with this kind of fracture. And this is a very common fracture, at least in developed countries where you have the population of the older population is higher. They are more prone to this kind of problems, having surgeries and so. And of course, it is involved for the same kind of process using a plated femur. In this case, a plate is a medical device to help the bone fracture. When you have let's say, a fracture in the bone, it's screwed in the bone until the reintegration of the bone, osseous callus, and this has also been used. In this case, you can see the difference between the experimental data and the numerical simulation is somewhat higher in this case. But this has involved for more recent work in vivo sensing of one of these factors. In this case, is a procedure that medical personnel use what's called a fixator. It's in this case is an external device. You can see there are some pins that enter the bone to go enter the tissue to go up to the bone, and there were brag ratings installed. One of these in the top here, and another one in the middle. There are 7, in fact, but there are only results of these 2 in this presentation. And they were measured in a period ranging from 2 to 8 months after the surgery. And particularly you can see that is the resonance frequency of these sensors. This resonance frequency was measured using a hammer with a strain sensor to measure the impact on the patient, so that it is some calibrated procedure, and then you see there as the bone became more stiff, the upper and lower part of the structure, they have a higher resonance frequency because of the stiffness. So that you can see there is a change in the bone structure along time measured by this kind of sensor. And we also use this in dentistry. It started using a cadaveric mandible that was instrumented by FBG sensors, both to apply a load to see the response, or a dynamic load in which a weight is dropped over the pin of a dental implant to see the response. One aspect that I talked very briefly in the beginning is that optical fiber sensors are quite small as compared to standard sensors. You can see here this dimension. Here is a strain gauge, a normal strain gauge. And in fact, in this picture you cannot see the FBG. But you can see this is the cable of the strain gauge. There is another one here. There is the cable. And here is the cable with the optical fiber going to the equipment. And the optical fiber came here. It's more or less here. So that you have a very, very small device that gives a more punctual response on the process. Do not average on the surface. And there are the responses of the dry mandible. We could measure the frequency. Of course, this is a rigid frequency because it's cadaveric, it's not a normal one. And of course, they do not show the damping of the visco tissues that we have between the teeth and the bone. But the signal to noise was very good, in fact, better than the use of the strain gauge complement. And this has evolved in a better model, in this case, not using a cadaveric one, but using a mandible that was manufactured using ceramic that reproduces the mechanical properties of the bone. So that is very realistic, is the kind that used in medical schools. And so in this case, several sensors were placed along the neutral line of the mandible, that one that usually do not deform in rest conditions, and another one is placed in the support, so that you can apply, let's say, by means of straps or wires that are here shown. You can apply different loads, and you can change the position of the load depending on the teeth. More or less like you want to crush a peanut. You can use your molar, or you can try it in the incisive or canines and so on. And again, this was used to validate a model in finite element mesh that's shown here. And let's say in terms of modeling, the response was quite good for different sensors here. And the experimental results also show the response of each one of the gradients, let's say the deformation in each section of the bone, depending on where the load is applied. And some you have contraction, some you have expansion of the structure on that one. And this has evolved to other models and other applications, for example, in orthodontics, starting with a common simulator that used in medical schools That's a metal jaw in which you have with some gum, and you have a model teeth to be placed like a normal structure of the human being, and they use it, for instance, to study the effect of the orthodontic appliances that are put to correct position of the teeth. Yeah, and from the initial, this initial model instrumented with the bracket, we developed another model. In this case, using a proper material, again, in this case, acrylic, dental acrylic, in which the gratings were fixed during the cure of the resin. You can see here there are where the place where some fibers are living, so that we have several gratings close to the teeth position here. So load can be applied at a normal or transversal to the teeth in different positions to see the changes in the structure well, this is different. This is not FBG sensor, but it's a nice picture. I put here. This is a normal sensor in which light is launched on a fiber. In this case, it's a plastic fiber, a polymer. And then, I believe it was mentioned by Alexander yesterday, you can measure the intensity of light. So that, in this case, here we have the orthodontic appliance, so that one that uses some straps to apply load that you see, like a helmet with some straps that came from the mouth of the person, and so that you can apply load and measure the intensity to obtain the force as a function of the load. So that is a process to help, let's say, the dentistry process of adjusting the orthodontic appliance in this case. And a more sophisticated work. In this case, you can see here one of our appliances that uses the small brackets that are attached to the teeth. There were gratings positioned on the brackets, so that it was possible to see the load on some teeth, in this case the incisive, central incisive teeth, as a function of the load on the straps of the apparatus. So that there are again nice use. And there were also some studies made in the dental implants using real bones, in this case ex vivo samples. And these are models. These implants are greater than a normal human implant. They are scaled, to fit the bone. The bone is from cattle again, And but in this case, it is a bone that is fresh. It's not a living one, but just after the death of the animal. And sensors were placed in several positions close to the implant in the longitudinal axis, close, measure the strain in longitudinal direction and in the transversal direction. So that, and these were done using different implants, metallic ones that are normal, that are used by dentistry, and but also some ones for that metal covered by a plastic layer or all plastic implant. The reason is related to that first experiment that I talked, that with a cadaveric mandible you have a response, a frequency response that has no damping, because it is a hard material. You don't have the soft tissue that provides damping when you are in normal mastigatory process. And this plastic is very used to see the difference in the stiffness of the material in the response with load and also with frequency. And this involved in this case also for a different measurement that was to look for the strain in the periodontal ligament. That is just the material between the teeth and the bone. Yeah. In this case, using again an ex vivo material, in this case a pig mandible, yeah, and the fiber with comes here, the grating was inserted by a dentist in a position close to the bone so that load can be applied. In this case, you can see what happens when you apply and release loads. You can see the response of the material with the load. And this can, with dynamic studies, can lead to a measure of the PDL properties. And this is quite interesting because the PDL in literature is well often mentioned, and it basically goes to a paper with the first result on the PDL value was a paper on the early 50s. Yeah? And they have some figure, and this has been replicated in several other peoples that if you make a tree of the citations using, for instance, Web of Science, you can obtain something like 20, 30,000 citations that are related to that original one. Well, the only problem is that more recently, about 10 years ago, they discovered that the original one was not correct. There was a mistake in the, let's say, change of units. So that the value that people were quoting for PDL make it so viscous as solid asphalt in the roads. There's very strong value that do not fit, but were mentioned and mentioned again. Okay, other applications related to bruxism in person, and particularly in this case, bruxism versus Botox. In this case, it's a botulinum toxin. Yeah? Bruxism is caused by a parafunctional masturbatory hyperactivity of the muscles in the oral process. Yeah? And then it causes involuntary clenching or grinding of teeth. Yeah? And this causes wear of the dental fractures or in restorations that have been previously applied, and eventually cause headaches, muscle pain, and so on in patients. And usually they are caused by anxiety, depression, malocclusion, or eventually genetics of the person. Mainly occurs during sleep, and you have several treatments that are either physiotherapy or physiological treatment, and with prescription of intraoral or interocclusal device, this kind of splints that I show in the first picture about the sensors. Yeah. And more recently with the application of the botulinum toxin A, called BTA, to relax the muscles. I want to only wish to remind that one of the first in vivo biomedical measurements was done with a BGG in a dental splint. In that paper, they were more studying the apnea process, not particularly bruxism or masticatorial process. But it was a question of. Okay. Hello? It's working? It was only a question of changing the objective of the work to use it to study bruxism, using bruxism splints in the case. And I have put again the original paper of 2001 to compare with a more recent paper. And you can see the evolution of the, let's say, scientific editing of articles in the magazines, in the journals. You can see the difference by the colors and effects of the photographs that are now available. In this case, like that original paper, we have some FBG to measure the pressure of the teeth, and there are FBGs to measure the temperature to compensate the response of the sensor because of different temperature inside the mouth. Yeah? And they are calibrated using modes of the patient mandible and maxilla. The splint is put in the middle, and then it goes to apparatus that apply loads at different temperatures to calibrate the sensor. And after this process is finished, we can put it inside the mouth of a patient. In this case, it was not a graduate student. It was a postdoc. And to measure the response, yeah? And this can be used during the sleep, to measure the involuntary changes in the process of the muscles during sleep. And this has been done to calibrate the process before a Botox application. Yeah. And then after, following the recovery process a long time. So that we have, this is the applied force that is applied by the awake patient. In this case, the instruction is to clamp the splint with the hardest force you can. Yeah? So you can see here the level of response, about 30 newtons in this case, before Botox, and then you apply Botox. Botox has a relaxation factor, so that the muscles relax. And then if you see that 1 month after the application, there was a decrease of about 80% of the force that the patient can produce. Yeah? And after 2 months, there is a recovery process. It still is lower than before Botox, but it still is better than in the previous month. Yeah? This is for the patient awake with instructed to apply the force. And this is sleep responses. Yeah? You can see that during the time of sleep, sometimes you have these speaks that are caused by the movement of the bones, contracting the splint. Maybe there are other movements that are not perceived, but those are the ones that we can perceive by the position of the sensor. Yeah? And you can see the inset, that the appearance of the inset is more or less similar to that one awake. After application of Botox, 1 month, you have, again, you can see that even the involuntary process has reduced the magnitude of the force. Yeah? And you can see a small change in the pattern of the process. And again, after 2 months, we have a recovery of the initial hyperactivity, and the pattern, in this case, is somewhat different, but this is not a constant process. So that, but in any case, it's possible to analyze this process. So that, and these are in case. Well, sorry, there is some delay in the process. And these are only to resume the graphs of the applied force, the original, and then during the relaxation process. And you can see that after, let's say even after 3-4 months after the application of the Botox, the level is resuming to the standard level before the application, but not completely reached the original process. Yeah. Okay. And this is possible to do a patient monitoring in the process. Okay. Okay. the other area that we can use this kind of sensors in the study of materials that are used in orthodontics. So I'm just in time. I will try to pass very fast on that. This started again in the beginning of the millennia, and initially using some resins and then gypsum, other resins and so on, cements and etc. That they are used in different dental applications, either for restorations, for instance, the resins, or cements in fixation of roots, crowns, and so on, or even in acrylic is used for temporary crowns or occlusal splints, as I show, or even molding of multiple implants, where it's necessary to obtain a mold of the position of the implants to make the composite prosthesis over. Yeah? And all materials in this case is for resin, but it's valid for other ones. They have a problem of shrinkage, when they are applied in some cavity, for instance. When they dry, there are some stress that can lead to small fissures between the material and the dental substrate. And these factors can facilitate the penetration of water or other contaminants that can either go to loosening the restoration or even to cavities and other diseases. Yeah, and we use the fiber grading sensors to study the polymerization of the resins and other materials. Yeah, and these are some data. I put it in homage to Alexander. We make it a routine to process the data. This is the raw data measured by the sensor, and this is after some signal processing to increase signal to noise. And then you can study for given the start, for instance, of the cooling process, where there is an increase of temperature and subsequent decrease. But you can also look for long term, let's say when the curing process is complete for different materials. Here is evolution of temperature also for those materials. And you can either use it for define protocols for the illumination of the photoactivated resins or cements, and you use the UV light to cure the process. In this case, there are differences when using a ramp activated device. Is usually a blue LED source that has a ramp, so that the intensity of light increases and then keeps constant for some time and some decreases, and or using a conventional lamp process in which the intensity is constant along all the time of the process. And this also gives different results on the final value of the deformation of the material. And again, this can be done in vitro, in loco. For instance, these are studies in materials that are either measured in glass plates, that's an external measurement, or inside the root channel. Well, the graph is the same. I can keep this one. Okay. And that in the previous slide, there was in the slide, the preparation slide, and then inside the one restoration. And here we have inside the restoration two positions: a cervical position close to the surface of the teeth, and an apical position inside the root channel when there is a pin, a post inside the process. You can see difference for both materials. You can see that the apical polymerization that's inside the channel is not so good as in the the cervical process because light do not penetrate so deep in the oh, now it goes away. You can see you have one sensor there, one sensor here, and here is a graph showing for the scattering of light that of course light can penetrate better in this region of the sample than inside the channel for the polymerization, this case that's activated. And also for the resin, the acrylic resins, there are similar studies, the molding, and well, let's go to keep the time to the conclusions. We can have FDG sensors that are both attractive and useful biomechanical studies, and these studies can go from in vitro situation up to in vivo situations, like patient care. Usually they are less intrusive than standard strain gauges, thermometers, and other transducers, but remember, the problem with the fiber is that you have a connection, so you have some cable. Of course, when you are sleeping, the cable can go to apparatus, do not bother so much. When you have a fixture in a factory, the cable is rolled in the fixture and it stays there. But obviously for normal day activities, it's cumbersome to have a cable there. Okay. But another advantage is that measuring units can be placed far away from the point of sensing. That's quite useful for clinics and hospitals in that you can monitor a patient from a central nursing station, yeah, using fiber instead of electrical cables. And you can have valuable results for validation of numerical models or point of care applications, materials, and clinical procedures. Yeah. We have several groups in Brazil working on that. I listed some that are more in contact with me, Espírito Santo, Federal do Paraná, Technological, Federal University in Curitiba, also State University of Ponta Grossa. I forget to mention here Federal University of Rio de Janeiro. They have a nice group on biomedical optical fiber sensors. Yeah? And there are other sensors that are being studied. Okay. This is only a remark to students. If there are students here, profit from the workshop. Don't be afraid to ask questions and talk to the persons and so on to recognize possible partnership. We have a long history of partnership with a group in Portugal since 1999, and that started because one PhD student of the came and asked me some questions, and then put me in contact with his advisor, and then a lot of. And I have to acknowledge the funding agencies in Brazil that support our work. There are a lot of colleagues and students that participate in that, and particularly I would like to add some personal record for the women working in sensing in these works from several of those universities that are mentioned along the references. Okay, and thank you for attending. See you.
We are just about to start the coffee, so we have a time for one question. Any question? Right.
So I'm familiar with using bioimpedance in my research. How hard is it, and I use wires, how hard is it to convert from wires over to fiber optics?
I say, in principle, converting from wire to fiber optics, depending on the instrumentation, it's easy way. You have to convert your signal in the optical domain and then sending it to a receiver and reconverting to electronic one. That's usually what, I say not all, but several sensors are done. In this case, the fiber is just an optical channel to transmit the information. Yeah. For instance, you see that in the mandible we have some standard strain gauges that basically is a resistance device. You measure the resistance of the strain changes, and you have an optical equivalent. In this case, it's a completely different detection process. You are detecting the optical response, not the electronic one. But for other instruments, you can send the optical information as transmission of signals. One problem with the electric and electronic measurements with human bodies in general, not human bodies, but in living bodies, is the question of the response. For due to evolutionary process, we all respond to optical frequencies. The reason is that the only frequencies in the surface of the Earth are optical in a very narrow band that's more or less what we call the visible. Some also in the infrared, but they're not so good. And this is because of water in the atmosphere. And so the response of the animals and living beings, even plants, for instance, chlorophyll process is induced by light, by visible light. It do not use X-ray, do not use microwave, do not use terahertz or other frequency. It uses optical frequencies. Yeah? And so it's somewhat difficult to measure a molecular parameter using electric electronic frequencies directly. You can measure, for instance, if you are making an imaging process, MRI and so on, you're using atomic frequency. This is characteristic of the atom, but cannot, for instance, detect, like I was talking with Alexander, the glucose level of the blood with electric frequency. Up to now, we do not have a good response that would show the sugar molecules responding to a radio frequency or similar. They respond to the optical frequency, and the optical frequencies are bad because they do not penetrate the tissue. They are absorbed by other layers of the tissue or by other materials. So that there are complementary sensing techniques, those based on electronic instrumentation and optical instrumentation. I believe that for the moment, maybe, let's say, the optical instrumentation can have a large share of the market with IoT, in which you can, if you can have a battery that will support the optical source for some time, you can make a measurement and then use IoT to transmit to a receiver linked to the network. That could be a good way to direct the sensing market. Don't know what I answer exactly your question, but it's my feeling.
Okay, thank you, Professor. And we are ready for coffee. Thank you. Okay. Are you hungry? Coffee break is being served. news about what's going to happen next. Nothing. Because we are supposed to have one a presentation now, oral one, the paper number ID 5, and there's no people here to present it. So we are jumping to the lunch. Okay. Sorry. Yes, more time for lunching. And we back at 1:30. Hello again, me again here. I know that you are sick of me, but I have to be here. I know also that you want to be on the beach, drinking coconut drink, but I'm afraid to tell you that we have to be here. And for the rest of the day of the conference, we are going to have two talks today, this afternoon. One given by Professor Orion Martinsen from the University of Oslo, which is going to be now, and after him I will give a tutorial about bioimpedance. And I'd like to welcome Professor Orion Martinsen from Oslo, who's also kindly supporting this event. Thank you.
Thank you very much. I'm just going to. Can we do a little bit like this? Yeah. Thank you very much, Pedro, and thank you for inviting me to come here. It's always a pleasure to come to Joinville and Brazil. I've been here sometimes before. We're going to talk about the four-electrode system today, and I think all of you who have been working with bioimpedance are very familiar with the four-electrode system. And you will hear things like if you are going to do impedance or bioimpedance measurements, you should use the four-electrode system. It's the best electrode system. You will hear things like that. I will try to complicate that a little bit to make that a little bit, it's not that simple. Let's see. So, the basic or most simple way to do an impedance measurements, whether it's on a biological material or any other material, is to use a two-electrode system. And just going to. And you can do it in either of these basic ways. You can apply a controlled current and measure the voltage, and then you can use Ohm's law to calculate the impedance. You will have a voltage which is proportional to the impedance, and if you measure the phase angle between the voltage and the current, you can calculate the resistance and the reactance. Or you could do the other way around. You can apply a controlled voltage and measure the current. Then you will have a current which is proportional to the inverse of the impedance, which is the admittance. And if you know the phase angle, you can calculate the conductance or the susceptance. And the susceptance or the reactance can be either capacitive or inductive. And in biological materials, you know, it's mainly capacitive. We do have some inductive effects at high frequency, but it's predominantly capacitive. It's not, if you want to measure impedance or express impedance values or admittance values, you should keep in mind that impedance is somewhat linked to a series model of the resistance and the reactance. You add together is R plus JX, so you add together resistive values, so it's linked to a model of a resistor in series with a capacitor. Whereas if you use admittance values, the conductance and the susceptance, they are more linked to a parallel model. So that's something to keep in mind. Then back to the four-electrode system. Because, let me say first, with the two-electrode system, you measure everything between the electrodes. So this thick black line could be the skin, for instance, if this is a biological material, and that could be living tissue. And you know that the skin, the uppermost part of the skin, the stratum corneum, is dead and conducts current very badly, at least at low frequency. So measurements tends to be dominated at low frequency by the skin, the uppermost part of the skin, and by the contact impedance. You have charge carriers here, which are electrons, and you have charge carriers here, which are ions. So you have to have some place where charge is transferred to or from the ions. So you have oxidation or reduction. So that is what you call the electrode, and that will have some specific impedance, which can be equally high as the impedance of the tissue that you are trying to measure. So it can be difficult in some cases to separate between the electrode properties, contact properties, and the actual tissue properties. So that's why people tend to want to use the 4-electrode system, because they get told that with the 4-electrode system, the electrode polarization, that contact impedance, doesn't play any role. You can sort of sort that out. But of course, you don't want to use a 4-electrode system if you want to do measurements on skin. In our research, we do a lot of measurements of skin properties, and you don't want to get rid of that. So if you want to do measurements on the skin, or you want to do measurements on electrode properties, so don't use a 4-electrode system, because you will not measure what you want. And there is also a combination of a 2 and 4-electrode system, which I will not talk about today, which is the 3-electrode system. It's sort of half of a 4-electrode system. You will have this on one side, you will have one electrode where you measure everything, and on the other side you will have what's more similar to a 4-electrode system. So with a 3-electrode system, you can sort of separate out one electrode and do monopolar measurements for that electrode. But that we will not talk about today. So there are many cases where a 2-electrode system is the best way to measure. So keep that in mind also. It's not always that the 4-electrode system is best. And the 2-electrode system is simpler. It's simpler to interpret the results also. As I will show you today, the 4-electrode system can be quite counterintuitive in many ways. It can give you results. It can give you negative resistance, for instance. I will show that today, which is not a measurement error. It's a correct measurement, but the resistance, the total measured resistance, is negative. And that's because the 4-electrode system does not measure a genuine impedance. It measures the transfer function of a system. So it measures transfer impedance, which is not the same as impedance. And I will use this lecture to explain this in more detail. This is the 4-electrode system. So instead of using only 2 electrodes where you inject current through them and measure the potential between them, you want to separate out, you want to use 2 different electrode sets, one for current, one for voltage. And that's exactly what you have here. So this electrode system is based on the work of William Thomson, also called Lord Kelvin. And it has 2 electrodes here where you inject the current. So you can see these continuous lines are the current lines, and they will produce equipotential surfaces like this. So these are the equipotential surfaces, the dashed line. So you have a known current flowing through here, and these 2 electrodes will pick up a potential. This will pick up this potential, and this electrode will pick up this potential. So you will have a potential difference, which you can measure with a differential amplifier. So you could basically say that in this area, which is limited by this surface and this surface, you know the current which is flowing, and you know the potential drop, the voltage drop. So that is where you measure impedance. That is the basic, very simple understanding and explanation for the 4-electrode system. You measure only between these two lines. So this here doesn't play any role, so you get rid of the skin impedance, you get rid of the polarization impedance. And these electrodes are currentless. There is no current flowing through them for an ideal amplifier with infinite input impedance. But for real amplifiers, the input impedance is not infinitely high, so you have to make sure to have a good differential amplifier. Typical impedance instruments have amplifiers with around 20 megohm. So you have to make sure that this impedance is well below that to not have any voltage division. So that is the basic understanding. And this is what we call in network theory, we call it a two-port network. There are two ports. This is one port for the current, and there is one port for the voltage. And for this kind of network, we talk about the transfer function, system function or transfer function, which is defined as the output of the system divided by the input. So it's an expression telling you something about what your device is doing to the signals, the output divided by the input. So here the output is a voltage and the input is a current, which means that by definition the transfer function is an impedance. That's why we call it transfer impedance. So, yeah. But it has some, the way I explained it, that you measure from this equipotential surface to this, is a little bit too simple. It's the first explanation you will get for the 4-electrode system, but it's not sufficient. It actually matters, if you do something here, you change something here, it will show up in the measurements. And why? Yes, because the equipotential surfaces will move. So if you place here, if you place something which is electrically insulating, let's say a plastic ball, there will be more equipotential lines or surfaces in this ball, so you will have a larger potential drop there. So you will measure a lower potential difference here, meaning that you will measure a lower impedance. And this is not intuitive. If you place a plastic ball, something insulating inside your material, you measure a lower impedance. That is strange. That is unexpected behavior. However, if you place it here, you will have more equipotential lines here. You will have a stronger field here because of the not so good conducting material. So you will measure a higher voltage. So then you will measure a higher impedance, which was what you would expect if you place something insulating inside your material. The impedance will increase. It will if it's here, but not if it's here. I will give you, before I go into these details, I give you a couple of examples of these kinds of measurements. I know there are some people interested in fish here, so I have one with fish. Sorry, bit dry mouth. These are impedance spectra measured on haddock some years ago, published in 2000. So what you see here is a fish bought live on the market by a student of mine. He took it on the subway up to the university, or he actually then killed it. Or in science you don't kill things, you sacrifice, or you use other words, but in practice that's what he did. and he took it from the harbor on the subway up to the university and started measuring with a 4-electrode system, 4 surface electrodes on the fish. So it's a few kilometers, so it took him a little bit more than 2 hours. I don't know if you can see, but the first measurement is 130 minutes, so it's 2 hours and 10 minutes after the fish was sacrificed. And then you see this curve. This kind of plot is known to some of you as Nyquist's plots. In bioimpedance we tend to call them Cole plots. In Norway we call them Wessel plot, because the Norwegian surveyor Caspar Wessel was the first in the world to plot in the complex plane, but I'll call them Nyquist plots because that's internationally what they are known as. So you plot the real part of the impedance, or you plot the imaginary part as a function of the real part with the frequency as a parameter. This is impedance, so this is from, I think it's from 10 Hertz up to 1 megahertz. So what you see here, I will not go into the bioimpedance details, but you see what we call dispersions. You see 2 circular arcs. One would be what we call the alpha dispersion at low frequency. These are ions, counter ions, moving laterally on the surface of the cells, the muscle cells. And this will be the beta dispersion at a higher frequency, which will be the charging of the cell membrane itself. Then things starts to happen. 1 hour later approximately we get this curve, and then this curve, and up here after approximately 5 hours we get this curve. Then I have repeated, I go further here to make it clearer to see it, so this is the same curve. Then the curve goes back, and after some 12 hours we are left with this small dispersion here. So from these measurements we can actually read quite a lot of physiology. What happens here when the low frequency impedance increases and then decreases is that the muscle goes into rigor mortis. It becomes stiff. The cells swell up. So the current at low frequency, which mainly flows around or between the cells, have less space to move in. So the impedance increases because there's less extracellular space because of the cells expanding. Then after some time it goes out of rigor mortis and the cell membrane starts to disintegrate. And then the alpha dispersion, which is cells moving laterally on the cell surface, they have less space to move on because the cell membrane disintegrates. So we lose the alpha dispersion. So this first circular arc disappears. And we are left with a small beta dispersion at the end. So you can read this physiology out of this kind of measurements. So in this instance, the 4-electrode system is very well suited for this kind of measurements. If we had done 2-electrode measurements here, it would be more dominated by the fish skin and so on, and we would probably not see these things as clear as here. Another example from medicine, this was a student project. I was teaching a course in sensor technology, and I made a student project for all the bachelor students in the course. So this publication in Sensors has some 30 authors, and most of them are bachelor students. What we did here was that we measured ECG, ordinary ECG, the electrical signals from the heart, and we also measured ICG, which is impedance cardiography. And that we do with the 4-electrode system. So for instance, if we want to measure over the heart, we inject current between this electrode on the forehead and this electrode down here. And these are ordinary disposable ECG electrodes, pre-gelled electrodes. And we pick up the potential difference approximately over the heart, somewhere here. We also did another, at the same time, simultaneously, another ICG measurement on the upper arm with these 4 electrodes. And we measure the ECG between that electrode and an electrode on the back here, down here. So you see here the ECG is the blue line, the ICG from the chest is the red line, and the ICG from the upper arm is the green line. And this is as a function of time. So people have been trying to use this ICG to measure cardiac output and so on. That's quite difficult. But it's at least very useful to use it for timing measurements, because the ECG is a measure of the electrical activity of the heart. The ICG is more a measure of the mechanical activity of the heart. And this is measured at 64 kilohertz, injecting 300 microamps, and it's the derivative, the first derivative of the impedance that we measure. So this first bump here is called a C wave in ICG. And in this study we did it on 10 younger subjects, typically students at our department, between 20 and 30 years old, and 10 older, typically people like myself, professors and so on. And we measured the time the pulse wave took from the chest to the upper arm. We also measured the distance, so we can calculate the speed. And the velocity, the pulse wave velocity, was significantly higher for the older group, indicating that the vessel wall is stiffer due to probably to arteriosclerosis. So it was a very clear and significant difference. So perhaps this can be a way to measure the degree of arteriosclerosis in patients. I don't know. So that are 2 examples where the 4-electrode system is very convenient and very well suited as an electrode system to use. But the transfer impedance, the 4-electrode system, has some peculiar behavior. I sometimes use this analogy. People think it's a bit stupid, but I do it anyway. So imagine that I put 4 electrodes on my leg in a row. I use the 4-electrode system and I measure the impedance. And I say, this is the impedance of my leg. Then I move the middle 2 electrodes, the voltage pickup electrodes, over to the other leg. And then I measure 0 voltage here. No potential difference, but I still drive a current here. So 0 divided by the current is 0 impedance, which means that I'm a superconductor at room temperature, which is quite, that's calls for a paper in Nature or something like that. No, it's obvious that this is not a proof that I'm a superconductor. It proves only that none of this current here is flowing here, so there's no current flow, hence no voltage difference. So that sort of shows the principle of the transfer impedance. It's a measure of how much of the original signal you can transfer to the other port. It's a two-port network. So by moving the pickup electrodes away, you don't measure any potential difference. Doesn't mean that there is no impedance there. Just means that none of the original signal can be picked up with that second port. So yeah. I would also claim that it's very difficult, perhaps impossible, to calculate conductivity, resistivity, or permittivity, any of these electrical parameters, material properties for biological tissue from 4-electrode measurements. The geometry is too complicated usually, and the way the different subvolumes in the material contributes is too unpredictable often. I will show you examples on that. Perhaps if it's a totally homogeneous, uniform material, that could be possible. So what we have used here is, I say here that it's not so often used. It's starting to become more common to use the finite element method to model these kind of systems. You don't have to use COMSOL multiphysics. There are a number of other programs you can use. We often use COMSOL multiphysics, and I will give you one example. First, one which is only DC, a DC example, and also 2D, so it's not extremely realistic. So none of us are in 2D, but it's an approximation, and it makes it simpler to show here. So imagine now that this is the material, the box is the material you want to measure on, and the electrodes are the 4 on top here. Since it's 2D, you have to imagine that all structures goes infinitely into the plane. So what we calculate is per meter in this direction. So what you do is what we call, how the basic question is, if you do a measurement, like this, how do you know the contribution from different parts of the volume? You would intuitively think that something up here would contribute a lot, but things down here in the corner will not contribute so much. And that's also true, but how can you put numbers to it? So there is a way developed by Geselowitz in an old article, so-called lead field theory, which we use here. And it's his theory I will go through here and show you an example. So what you do according to his theory is that you first inject a current between the outer 2 electrodes. Then you calculate, or you let your finite element program calculate the current density vectors in all the small subvolumes, in all the voxels, in all the elements. And you call them J1, for instance. Then you do the same for the voltage pickup electrodes. You inject a current between the voltage pickup electrodes, and you let the current electrodes be passive. And you again let the program calculate the current density vectors in all the voxels. And you can call them J2 then instead. Then you can calculate the sensitivity for that by making the dot product in the voxel between the 2 current density vectors. And the dot product produces a scalar, and it's, as you know, this times the cosine of the angle between them. This shows the reciprocity behavior, or the reciprocity theory says that you can instead of injecting current here and picking up voltage here, you can inject current here and pick up the voltage here. You will get exactly the same result. And that is also quite counterintuitive in my mind, but it actually works. We do that sometimes, and you do get the same result. And that you can see here, because it doesn't make any difference between the two current densities. If you divide it by the square of the current, if it's the same current you use or a unit current, you get a scalar number in each element telling you if it is a uniform material, how much, relatively spoken, that element contributes to the total impedance measured. If it is not a uniform material, you have to calculate with the local resistivity. Now this is a DC case, but if it's AC, you have to use complex resistivity as a vector. And you do that for all elements, and you sum up all the elements. That will give you the total impedance measured. Or here, since it's a DC case, the total resistance. But if the angle between the current densities is more than 90 degrees, you will get a negative number. So sensitivity can be negative. And that gives this counterintuitive behavior that if you put an insulating object there, you will measure a lower impedance in total. That is typically between the voltage pickup and the current injecting electrodes. You get zones of negative sensitivity. And this adds to the sort of strange behavior of this system. And it's impossible to get totally rid of the negative sensitivity zones. You can minimize them, but you cannot get rid of them. So here's an example. Here is a plot of the sensitivity. Now this is a uniform material. I can zoom in. You see 0 is here, so this is negative sensitivity. So all these dark blue areas have negative sensitivity, meaning if you put a metal here, well conducting, you will measure a higher impedance. You put it here instead, you will measure a lower impedance. So this is not so easy to predict always. If the material is not homogeneous, you can do like this. Here I have put a slab here, which has higher resistivity, only 20% of the conductivity of the surrounding medium, so it has 5 times as high resistivity. So this is DC, remember. This is the sensitivity plot. And now it doesn't any longer tell you where you measure, because it's not homogeneous. You have to multiply with the local resistivity, and you get this plot. So now you can see that these parts here will contribute the most to your measurements. So this is what we call volume impedance density. And then you can play around with this. You can increase the size of the electrodes. So you can see what effect that has. You can move, here I have moved 2 of the electrodes to the side, so these are now electrodes, which makes the sensitivity or the measurements go a bit deeper. You can increase the separation of these electrodes, still having current injecting electrodes here, which also make you measure more through the whole material. And remember, you can equally well now inject a current between these and measure voltage here. You will get the same impedance. With a closer look. With a 2-electrode system, you can use the same mathematics, of course, but it's the same electrodes that is used for current and electrode. So J1 will always be equal to J2. It's the same electrode set. So it's only the square of the current density, which is always positive. So you cannot have negative sensitivity with a two electrode system. You see 0 is here. So that is it totally. So negative sensitivity is connected with more than two electrodes. A 3 electrode system, 4 electrode system, or this, which has been developed in Bangladesh, this focused impedance measurements with 6 or 8 electrodes by Professor Rabbani and his group. So I'm going to show you another simulation or modeling. We are now doing experiments where we try to validate this. It's not so easy because you don't always know exactly the electrical properties of the different layers. We know approximately, so we cannot validate it very exactly, but we use ultrasound to measure the thickness of the different layers, and we try to, so that is an ongoing project. But we have made this model in COMSOL, and it's a layered model with 4 electrodes on top. And you will see that in some cases we have this increasing thickness of the different layers, and we can give the different layers different electrical properties, and we can calculate what the total impedance will be, and also what the contribution from each layer is. So that's, yeah. And we have compared for a 4 electrode system, but we also calculate what we will get if we do a 2 electrode measurement between the 2 outer electrodes. So the volume impedance density for each voxel is given by this expression here, not so meaningful, but we calculate first the complex resistivity by using the version of Ohm's law where we get the resistivity by dividing the electric field by the current density. So we do that in all 3 directions and divide by 3. It's because some current will flow horizontally, and then it would be 0 if we used only that component. So we take the average of all 3. And then we do the dot product between the 2 J1 and J2 here for all the 3 different directions. So this is the way we calculate the volume impedance density, and we just sum it up. We can sum it up for the whole model, then we get the totally measured impedance, or we can sum it up for only one layer to see that layer's contribution to the total impedance. Then we have 4 different test cases, 1, 2, 3, and 4, where in case 1 the thickness is increasing, like we see here. In case 2 we have equal thickness for all of them, but the total model is only half as high, half as thick as this one. Then we have another one, third one, where we have increasing again, and then we have constant thickness, but the double of this, so it is as thick as this relatively. So for the first, we have alternating electrical properties with the conductivity here and the permittivity here. And you see every second layer has the same electrical properties. Then for the second, with the same thickness, we have the same alternating properties. Then we have increasing thickness with equal properties for all of the layers except for the top layer, which is better conducting. And that goes for number 4 also. Equal properties for all the layers apart from the top one, but we have equal thickness also. I've chosen to plot it in this way. I don't know if it's intuitive for you, but the black arrow is the total measured impedance in the complex impedance plane. So this is the resistance and this is the reactance. So this will be the phase angle. So here the phase angle seems to be around 45 degrees, something like that. And these are the contributions from each of the layers. And I've added them together as vectors because that's what we do according to the equations that we saw earlier. So we both add all these together and we check to see that we get the same as if we integrate over the whole volume, which we do. So it makes sense. This is the 2 electrode measurement. This is the 4 electrode measurement. Here you have a thin layer on top and then increasing thickness of layer. We have alternating properties, but we have a better conducting layer on top. And for the 2 electrode system, you see that the top layer, which is better conducting but quite thin, dominates in the impedance. You could believe that for a 2 electrode system, a thin layer, well-conducting layer, will not contribute so much to the impedance measured because it conducts so well. But this layer is very much in parallel, and that is the problem with these kind of measurements. All the layers are partially in parallel and partially in, but also partly flow laterally like this, and then the layers are in parallel. So the equivalent circuit here is a bit complex. And if it has been only in series, if you had one electrode in the bottom and one on the top, then this layer would contribute very little because it conducts well and it's in series, and the measurement will be dominated by the highest impedance. But a lot of current is flowing horizontally here, and then it will be dominated by the layer with the lowest impedance. So it's not always so easy. So it conducts well, but it dominates the impedance. And then you see as you get further and further down, you will have less and less contribution. For the 4 electrode system, it does not contribute so much. Actually, layer 2 contributes more. But the behavior is sort of understandable. Let's go to the next, where we have equal thickness. All the layers are equally thick, but as with the last one, we have alternating properties, so we have a better conducting layer on top. Here the top layer is thicker, and it dominates very much in the 2 electrode measurements because of the current flowing horizontally. And then the other layers only contribute a little bit. For the 4 electrode system, you have, it's actually dominated by negative sensitivity. So the first layer contributes quite a lot, but with negative resistance. And now it starts to become quite counterintuitive. This is not what you would expect. And then the other layers contribute in a more understandable fashion, and the total impedance is still with positive resistance. So you wouldn't expect something strange with this measurement. For test 3, we are back to increasing thickness, a thin layer on top. All the layers have the same electrical properties, except for the top layer, which conducts better. You see here again top layer dominates totally the measurement because of the current flowing in a lateral fashion. The current is going horizontally this way. So that is the dominant current, not the one going down here. If most of the current would have gone down here and up again, then this layer would contribute very little because it's well conducting, and it would be in series, but it is not. So it's totally dominating. Again, for the 4 electro measurements, it's also to some extent dominating, but with negative resistance. And then the next layer has predominantly positive sensitivity, and it all adds up to a positive resistance in the total measurement. The last one is equal thickness, equal properties, but better conducting top layer. So we have a better conducting and a somewhat thicker top layer now. And now you see, for the 2 electrode measurement, it's totally dominated by the top layer. All the current, almost all the current flows in the top layer horizontally. And the same for the 4 electrode system, but the top layer has predominantly negative sensitivity. So both the top layer has negative resistance, but the total measurement has more than minus 90 degrees. So here you would measure an impedance with minus, let's say, 110 degrees. You will measure a negative resistance, and you would believe that, okay, these measurements are not good. There's something strange with the impedance analyzer. Perhaps I didn't have good enough contact with the electrodes, something like that. But it's actually a good measurement. It's a correct measurement. It's only that this is transfer impedance. You will never see this behavior with the 2 electrode system. The 2 electrode system will never go outside plus minus 90 degrees, but the 4 electrode system can do that. Then we are approaching the end. So the basic message here is, when you use the 4 electrode system, don't be afraid to use it, because in many cases it gives very good results. But keep in mind that it is transfer impedance, and that is something different than impedance. In many cases that doesn't matter. It's okay, but it is actually a measure of how the signal is transferred from one electrode set to the other, and can give very counterintuitive results. I want to mention that we run the Journal of Electrical Bioimpedance. If you do bioimpedance or related work, please use it. You find it at bioimpedance.net. It's an open access journal. We are indexed in Scopus and PubMed and etc. And this is my research group, a little bit old photos. There have been some few changes. We also wrote the bioimpedance book, the first edition in 2000, then 2008, 2015, and last summer we gave out the 4th edition of the book. Thank you.
I have the 4 books. Okay, I don't know how, but I have the 4 one. Any question? I have some, but I will let you people to start. Any question? Right.
Thank you for the nice presentation. I wonder if this 4 electrode measurement system is analogous to the Van der Poel method for DC current. And second question, if the 3 electrode system is what is used in the electrochemical impedance, because you have three electrodes, the reference, the counter, and the working electrode, so it would be a three electrode system then.
Yes, to the first question, the van der Pauw method. I haven't used that myself, but as far as I remember, you have a square sample where you put the electrodes in the corners. So I guess that is based on the 4 electrode measurements, and that is a way to calculate the electrical properties. So it's a way to sort of get around these problems to be able to calculate material properties. So probably yes, it is using the 4 electrodes, but I don't know it so well. So I have to be a little bit careful. But I think yes, that is perhaps a way of using the 4 electrode system to get the material properties more accurately. And for the 3 electrode system, no, you're thinking about electrochemistry, I mean, to like use for cyclic voltammetry to measure oxidation and reduction. Yeah, which is a wet method. So no, it's not the same. When I'm referring to the 3 electrode system, I'm more thinking about ways of measuring on the skin. There is a specific circuit that we use with an operation amplifier to make sure the measurement voltage is in the better conducting skin layers, so that it's only a method that we use to measure skin properties at low frequencies. It is somewhat related, but there is two different systems, I would say, yeah, because you don't actually do impedance measurements with the cyclic voltammetry.
Can I do one more question?
Yeah.
And finally, how do you choose the material for the electrodes? Because probably it will have a difference in conductivity. You maybe have a metal and some dielectric, and does it matter what metal or which material you choose for do the measurement?
Yes, it does. I mean, it depends on the frequency range. So if you are measuring at a low frequency, you will typically want to use polarized electrodes, which is typically silver chloride electrodes with a gel. And it could be a solid gel or a wet gel. If you want to do measurements on skin, you don't want to use a wet gel because it will penetrate and change the skin. So these are very good and stable at low frequencies, because the pure metal electrodes are more DC unstable. But if you are doing higher frequency measurements, metal electrodes will often work well also. The polarization impedance is different for different metals. So we know that, for instance, aluminum is not a good metal for doing impedance measurements, but we often use stainless steel, and of course silver and gold and platinum. They are more expensive, of course, but often you can use just stainless steel, and we do that from 100 hertz and upwards. But if you are in a low frequency, you would like to use some non-polarized electrodes, because they have optimized the transition from the electrons to the ions by using first silver and then a chloride layer on that, and then a gel with a lot of ions and so on. So you have a very well-defined transition there.
Thank you.
Thank you. That was great. So kind of as a follow-up, so lower frequencies like iron would not be something good to use as an electron. I mean, as an electrode. Is that correct? Like a
Iron? No.
iron.
Iron. No, but we have made instruments where you use metal electrodes down to, as I said, around 100 hertz and below that, and that works well. We have found out that the polarization impedance is still much lower, especially if you measure on skin. But if you want to measure on some wet material, on living material, I think I will not choose metal until you get way much higher in frequency.
But stainless
It depends.
Stainless is fine. Stainless steel?
Stainless is fine, but it is a polarizable electrode. But yeah, it depends on the application, and it depends on the size of the electrodes. If the electrodes are small, things become worse. So it's difficult to give some exact answers, but in general, you would want to use metal for measuring at a bit higher frequencies and for measuring on materials that has a quite high impedance. If it's low impedance and low frequency, it tends to be better to use non-polarizable electrodes.
May I ask one more? And so the layering was super interesting. And so,
Yeah.
Is there a model that you or somebody has created where you can, and I know that your MATLAB that kind of does that, but is there a program where you can adjust the electrode diameter and the distance between electrodes, say on a human body, to focus in on a particular layer that you're interested in, say like
Yes.
upper thigh muscle?
Yes, you can do that, and we typically do it in the program called Multiphysics from a company called COMSOL. But there are other programs,
There are.
and
Okay.
some of them are free also, of charge, as far as I know. But it's very easy to do in COMSOL Multiphysics. But I mean, we heard in the last talk of examples of using finite element methods. So there are many groups doing this with different software. Yeah.
And that way you could focus on a particular organ, for example.
Yeah, so
like
you
the
can
heart.
make a model. I mean, you cannot make. You have to make some simplifications, but you can decide the level of complexity in your model. So this is, of course, a extremely simple model, but there are many people making models where you have different organs, so you can go down to a certain level, but you cannot model every cell, of course, but so you have to make some approximations.
Thank you.
When you're measuring impedance on the skin, does the person's temperature change what you're measuring? Like if the person has a fever, or does sweat make any difference?
Yes, absolutely. The sweat does change a lot because the sweat ducts are like shunt paths through the stratum corneum, so that's why we measure the electrodermal activity. We have a lot of work going on, and we had for many years. We actually had a company selling instruments to measure electrodermal activity. So that's when you measure the conductance of the skin of your palms, where you have this psychological determined sweating, not thermal as on the rest of the body. So that is due to the sympathetic nervous system, of course. So that changes the conductance a lot. The temperature does influence bioimpedance measurements. Typical values that are often cited, I don't know how exact they are, but for the conductance 2% per degree, and for the permittivity minus 0.5% per degree are typically values that are cited.
The reason I'm asking is that one thing I thought would be interesting is to try and detect sepsis. Sepsis happens when people have infections, and it's one of the largest causes of death in the world. I mean, almost half of the people who are in a hospital in an intensive care unit have sepsis, and it changes the blood circulation, it changes temperature, and detecting sepsis early can save a lot of lives. So I wonder if sepsis would cause differences in impedance being measured either on the skin or on mucosal surfaces, and if you could create something to detect sepsis earlier. I think that would be
I
quite
think it will,
interesting.
but perhaps bioimpedance is not the preferred method to measure temperature.
It's not a matter of measuring temperature. Sometimes the patient has a fever, sometimes the patient doesn't.
Okay.
But since there's a decrease in blood flow and there's less blood coming to the tissue, maybe that could change impedance. I'm thinking.
Absolutely.
And if there is something that is useful at detecting sepsis early on, it could save several hundreds of thousands or millions of lives every year.
Yeah, that's interesting. Yeah, thank you.
I don't know. Well, we cannot measure temperature with bioimpedance, but you can measure inflammation. Easy. And people have been using some patches, electronically flexible patches on the skin, and you can live with that for a long time, and you can release the data using RF, and then you can monitor what happened with the inflammation as you have the inflammation, as also for burning tissue. As your treatment's going well, the burning surface is being healed, you can also use bioimpedance. Easy. But my question is not that. My question about this volume. Well, we are talking about electromagnetic wave. Light, we know. For example, for light, we know that from one layer to another, we have a reflection. And I've published one paper.
Yeah, but I mean, we are talking about low frequencies here. We are far from the wavelength of the. I mean, we are in the near field here.
Right.
It's no electromagnetic field here, or no electromagnetic wave.
Okay.
There are electromagnetic fields, of course, but there is no electromagnetic wave here.
Let's change my question. When you move from one layer to another, right at the junction between one layer to another, there will be a reflection of the field, because you are changing conductivity or resistivity from one layer to another. So we are struggling the electrical field from moving from one layer to another, so there will be like a reflection back. And the modeling doesn't take this into account. Is that right, or I'm wrong?
I think you are again thinking about much higher frequencies.
Okay.
This is, I mean, reflection and this line theory with 50 ohms termination and things like that is higher frequency. So I think we don't have it. It doesn't play any role here. I would claim.
The last paper I published in my PhD, it was in 2001, a long time ago.
Yeah.
And I came out with this sensitivity stuff using MATLAB, not Console. We didn't have Console at that time, so I have to learn how to play MATLAB. Very, very hard. Play 3 loops in one looping inside another one. But anyway, I found a negative sensitivity, and my my find was the depth of negative sensitivity goes up to 1/3 of the distance between the electrode, the pair of the electrodes. So Hilton Brian Brown, my ex-supervisor, the first electroimpedance tomography in the world was developed by the group of Sheffield, as you know, was built in USA. And he said, why not we reject the negative sensitivity area? Let's stick a hydrogel right on the surface and let the negative be inside of the hydrogel, not in the tissue you want to. And we've done this measurement and worked pretty well.
Yeah.
It was in 2001, and I have not done any work since 2001 about that. So yes, we can move the negative sensitive out of the area you are interested in.
Yes,
Just
I know
moving
the
the
paper.
electrodes. Yeah.
I read the paper actually last week, so I know that work. It's very good.
But I know that the signal behind the layer, which is tissue, is a bit weak, because the stronger field will be inside the hydrogel, not in the tissue. But at least we remove the negative response. And we can play, for example, if you look into a cancer, cervical cancer, the cervical cancer tumor start at 40 micrometer below the surface. And if you want to look at the cancer cells, you don't want to the field goes to the millimeter depth. So you have to concentrate up, and then you can move the electrodes. In that case, 4 electrodes, I'm afraid. Yeah. And also we can do a trick in the electronic, pushing the field down also, in order to avoid the surface. Because yes, surface sweat, you have a short current, and this is a nightmare, of course. Nice issue, I like a lot of that. We can talk more, but we have to move. Thank you very much.
Thank you.
So we are 15 minutes late, and that means I'm going to finish 15 minutes earlier. Okay, good for me. Huh? No question. So that's me, younger, of course. And if you don't know me, I'm Pedro. I am full professor. I don't know if that's title is. Here in Brazil, saying full professor is like, we say titular professor. And I'm master degree on biomedical engineering and a PhD in the University of Sheffield on biomedical engineering as well. And I've started, I came to Brazil in 2002, helping a group in São Paulo to build the first electrical impedance tomography in Brazil. And it's a company that you can type on Google called Timpel, Timpel, Timpel. That means impedance, okay? T for tomography. And they are big company now, selling a lot of electrical impedance tomography. It's the only imaging technique used, imaging technique used in intensive care unit. There's no medical equipment allowed to be in an intensive care unit using image. Electrical impedance tomography is the exception of it. You cannot get a patient out of the intensive care unit for taking a tomography, X-ray, CT, all the stuff. Tomography, impedance, you can do that because for a lot of reasons that I'm going to explain you. So I'm going to speak to you about other stuff, and which is biospectroscopy based biosensing platforms. Why? Well, because the event is about applied biosensing. Introduction theory of electrical impedance spectroscopy, wearable sensors for GCM, this continuous glucose meter, continuous glucose meter, GCM. Signal processing and data analysis, clinical application of electrical impedance spectroscopy, and challenge and future direction, and a bit of conclusion. Okay, nice photo from IA, artificial intelligence. Well, this photo shows that where we can put the sensors. Almost everywhere we can put a sensor in chair, wall, bedroom, for measuring a lot of humidity, temperature, localization, and presence. And biosensing platform, and then in a sense are analytical tools actually that detect and quantify biological molecules or process. So biosensing are analytical tools. Spectroscopy. So spectroscopy is one of the techniques that you can use for measuring the response back from a biosensing system. You can use light, Raman spectroscopy, okay, mass spectroscopy. In that case, spectroscopy, electrical impedance spectroscopy, because spectroscopy, that means not only electrical spectroscopy. Spectroscopy techniques are widely used to analyze biological samples, and some people say biospectroscopy because it's applied for biomaterials. But you can use spectroscopy for analyze cement, the quality of, you put sand, cement, bricks, water mixed up, you have a concrete. Is that right? How good is a concrete? There's a company in Sao Paulo, can you believe that? Measuring the quality of concrete using spectroscopy. How bad is that? So you can use spectroscopy for measuring fractures of materials like concrete, walls, and in that case plastics as well. And also you can use spectroscopy to see if you have a short circuit in a circuit board, because they build circuit boards in thin layers, and the lines of the circuit board may be very close together and can be rusting process. And the rusting process, the copper can invade one line of the board to another line, and you can measure, detect if the board is okay, using spectroscopy. In our case, biospectroscopy, which is a study of interaction between electromagnetic radiation and the matter, and has been successfully applied to in biosensing. So people have been using a lot over the last 40 years. I started doing my PhD in 1999, and when I arrived in Sheffield, people was studying biospectroscopy over the last, on that case, 20 years. So, and they started applying DC current in soil. So this started in geology. They used DC current in big electrodes, put in a soil to see petroleum, water underneath the earth. So they started with that. So why not using tissue in people? And in people, you cannot use DC. DC current burn the skin. and you are in trouble with the standard IEC 6061-1, safe. People goes to the lab or goes to the clinic to do some measurement and leave the clinic burned. Cannot do that, can you? So that's why you come out with, well, we cannot use DC, you have to use AC current, alternate current. So applications in healthcare, agriculture, environmental monitoring, food safety, drug discovery, forensic science, biodefense, biomanufacturing, nanotechnology, and so on and so on. So the application area is very broad. Okay? Even to understand if the diesel contains soy oil or not. You know that people have been cheating, putting soya oil in the diesel. Semi-color, kind of same density, a bit different, but they put some nasty material and you pay for diesel. Is not, it's for cooking, yeah. And you can use spectroscopy in that case. And as you can see, as in terms of the evolution of a biosensor, we back to the 1956, the oxygen sensor. And glucose biosensor, for my surprise, starting quite a long time ago, before I was born in 1962. I was born in 1970. And urea biosensor, we have a microbial sensors and needle electrodes starting in the 80s. And bioreactors, people have been using a lot nowadays. Bioreactors for example, to monitor if the cells is growing properly. People extract cancer cells and put in a bioreactor to grow up the cells and put some marks to see the marks is good for killing that specific cell. My mark is my mark, your mark is your mark. So cultivating the cell in a bioreactor is good, a way for finding the good biomarkers for you in order to do the radiotherapy, for example. And that we can monitor using bioimpedance. Bioimpedance, or I'm saying biospectroscopy. And then back now, we are using nano biosensors. Now everything is going to nano. No? A couple of years ago it was micro is good, now it's nano. So if you put nano in a project, you're going to be approved. Yeah, nano, green, now green, everything's green. No? Free of carbon, CO2, now it's good. No? Don't travel by airplane, they burn a lot of CO2, go by bicycle. Things like that. So now we are using, we had one project which was rejected, I mean approved but not enough to get a grant. Yeah. There was a cut line in 9.1 and we got 8.72, so below the threshold. So, and we were going to use nano sensors, aptamers in a nanofiber, nano rings of gold, and again nano, looking for searching for dengue, virus, Zika, Ebola, whatever mosquito disease. And the element of a biosensor, as you may know, you have the sample itself that you want to analyze. Cell culture can be a human sample, blood, urine, saliva, okay, food sample, or air, water, soil, vegetation. And you have to have a transducer converting the sample. You need a transducer to react to the sample. It can be a bioreceptor and electrical interface. And bioreceptor can be an enzyme, antibody, cells, nucleic acid, DNA. And you need to have an electrical interface. Can be electrode, nanoparticles, nanowires array, FET, field effect transistor device, as ion FET. You know, the one they are measuring glucose level that you can buy from Abbott or Dexcom. They put electrode here, and you stick with electrode and leave with 10 days or 2 weeks with electrodes on it. There's a needle. And they release a tiny strip of textile product underneath the skin, and they react with the glucose on the blood, release peroxide of oxygen, and the peroxide of oxygen is the responsible to make the fat to transmit and convert to a potential, DC. And DC is directly proportional to the amount of peroxide, which is directly proportional to the amount of glucose. That's why they do it. And that both is converted to digital, put into a memory that you can release anytime you want. This is FAT device. And also after that, of course, you need the electronic system to convert this into voltage. We need to convert to voltage, so you need a transducer. Nothing can be done without a voltage. Okay, we have to put somewhere, we have to work with, we have to process it. We don't process current. Well, if you want to send a signal from this part of the room to other part of the room, better if you do in current, of course. That's why from Itaipu, big hydroelectric energy, from here they come by wires, and we lose a lot of energy. Yeah, a lot of energy coming by voltage, and we drop, and come here almost that much. That's why energy is so expensive. Okay, most of the country, but here is kind of half and half. So we have to convert to voltage, and we use a lot of processing, signal amplifiers, electronic, all sorts, all type. Well, application of the platform, as I said, I'm going to jump some slides in order to not to be so repetitive. Healthcare, diagnosis and monitoring disease, drug deliveries. So, as I said before, just a point here, detection of bacteria, pathogens such as Salmonella, Listerine, E. coli in food samples is possible. And I've been seeing a lot of papers in sensors. If you want to have download some papers free, because we pay to publication, is bloody hell expensive, you know. Sometimes it's $2,200. Anyway, I'm not going to that issue, but you can download a lot of biosensor application using a lot of techniques, including bioimpedance. So the application is you have a functional brain, for example, neurodegenerative disease, and neuropharmacology as well. People have been using nowadays because biosensor is appearing a lot now. People have been using a lot of biosensor, but you have to read the response of biosensor, and using spectroscopy means that you can measure without damage the biosensor itself, because it's low cost as well, robust, effective. You can wear the technology. And detection of antibodies is the other one. Yeah. So resume of it is, as I said, soil, environmental, disease detection, water monitoring, if the water is good or not for drink. Toxin detection, drug delivery, pathogen discovery, and food quality. So you can use spectroscopy in all of it. Everything that is bio can be bio. You can use electrode itself, but you can also now use biosensor. You use a metal electrode, can use a carbon electrode, nanotubes electrode, but also you can put a layer of chemical substance in order to react and have the affinity of something that you want to detect. If you want to detect COVID-19, you may, for example, as we have been doing, we are printing out electrodes made of graphene. That's easy to print, easy size, shape, and you create a cave, a square on the middle of the electrode, and you are putting biotin, streptovidin, and a copy of RNA of the virus, safe. And then when you put a sample of the blood of someone that you want to examine, then if contains virus, that means the binding will happen a lot with the copy of the RNA of the virus. That means you are covering the area of the electrodes. And using spectroscopy, you can calculate the covering area of it. And that number, you give a sense number that say, oh, truly positive. But also it can be false positive. But at least you can have, say, okay, it's positive 100% sure, or negative 100% sure. And it's also easy to do, robust, effective, low cost. You can do in a device like that big. And also you can send all the data to a mobile phone. So see, you cannot do it using light, Raman, other types of technology. And that's it. You have the analyte, the bioreactor, the transducer itself, the electronic, and display can be in a mobile phone, a computer, PC, desktop, can be in a tablet, any type of interface. And we can use as a bioreceptor, as I said, all these. And we are here actually. You see how many transducer that you can use? Electrochemical one. We are based on electrochemical one. Electrochemical, you have amperometric, potentiometric, voltammetric, conductometric, and impedometric. That we are here. I'm here. I'm using impedometric. But also you can use optical ones. You can use thermal one, electronic one, galvanometric one, acoustic one. So a lot of techniques. Each one has an advantage and a disadvantage. Okay. I'm not going through that anyway, but some techniques are more expensive than others. Someone you can wear it in your body, and some other one you cannot. It's almost impossible. But I've seen some devices in how to say in a city in Italy, Florence. ATTD 2024, Advanced Technology and Treatment on Diabetes. It's a big World Congress. The next one will be next year, of course, in Amsterdam. I've seen companies there using RF technique, using Raman in a watch that big. So the battery is big. Raman technology, measuring blood glucose, using Raman technology in a tiny watch. Big battery, but you see RF as well, using waves like coming from 0.6 gigahertz up to 6 gigahertz. Expensive technology, a bit. So the world is like that. People have been trying a lot of the solutions. In my case, in our case, I'm using impedometric. Why? Well, because I've learned. That's why. So to learn new stuff demands time, and I'm old for learning new stuff, starting from scratch. So let's stick with what I've learned since 1999. And as I said, the transducer can be can be a polymer, not only a metal, can be nanowires, nanoporals, and recognition element, as I said, a nanomer can be, in my case, we use for COVID-19 streptovidina. Streptovidina is a monomer that can be used as a recognition element. And that's one potential stat device that I don't have it, but I have another one. When you are looking for electrodes, playing with electrodes, it's good if you have a potential stat in order to do a voltammetric data, to see you can change the current, you can change the voltage, you can, and to see how high can you go and what's the minimal in terms of sensitivity of the data, and see if the electrodes can be returned. Can you back to the normal stage? For example, you put a lot of solution in your electrode, and if you dry it out, does it back to the same response? Can I use again the electrode, just wash it out, or you need to dispose the electrodes? So voltammetry is good for that. And at the end of the day, we as Professor Orion said, at the end of the day, we have this, measuring the impedance, okay? We have to have a model, because we have a curve which can be fit as a polynomial curve, but is not integer order. It's not a polynomial of order 2, 3, and 4, and 5, and 6, and so on, but is the order of the polynomial is 3.5, 2.8. How can you represent that? That's why the brothers came in 1941, called Call and Call model. Two brothers. Okay, one is the brother of another. I'm just kidding. But 1941, they came and said, wow, hang on, let's put a non-uniform parameters over there, and let's find the alpha which fit the data to the model, and that they came with that. And we usually do this, imagine a real part, imaginary part, and as you can see, is a nice, bizarre, very low frequency, almost a straight line, and now we have a reactance starting to play a role on it. And people studying electrodes, they are more interested in that area other than this. Okay? If the contact impedance is good, and how big is it? And we need to do this model because at the end of the day, we need to extract the parameter resistance, capacitance of the system, the equivalent one, and then these parameters we can play with that and get a number. Let's say we can calculate here the frequency corner of it, where the impedance start to change the signal, start to change the sign of it. That's the frequency corner. No? The dispersion, alpha, beta, as Professor Orion said. And from that we can say some characteristics of the tissue, of the sample. If you have a glass of milk, cow milk, and the milk is not good, contains too much somatic cells. Okay, too much. You're not supposed to drink that. Somatic cells, that means cells. a lot of somatic cells give you a equivalent capacitance that big. So the dispersion in the field will be big. So depending on the dispersion and the cutoff frequency can give you a good sign that's, oh, that's milk is not good. But also you can plot real and imaginary part, and this radius will change as well. So people have messed up something. For example, these terms, electrical impedance spectroscopy. Someone say bioimpedance analysis. Are they equal? What do you think? They do like similar? Other ones say bioimpedance spectroscopy. There's a lot of terms in the literature that's bioimpedance analysis is for body, is more for conventionally, more for body composition. That you go to the doctor, to the specialist, and you pay about $80, and tells about the free fat mass, the amount of water content of your body, about what you have skeletal mass, free fat and fat mass as well. I don't believe in that measurement. Sorry, for me is a magic. Okay, for me it's a magic analysis of the body using someone use 2 electrodes, someone use 4 electrodes, someone use one frequency, someone use 2 frequencies. They put you, they measure you, how high you are, the weight you are, and they put something measure here, and they put in a formula, sum up, that's the number. And you are bad, man. You are bad, you're fat. Oh, don't tell me, I can see in the mirror. Yeah, but something like that. Yeah, and you pay for it. They pay for it. 400 reais here in Joinville. 400 reais. My wife paid, I can't believe that. Yeah, but anyway, how do I say? I want to be happy. So, electrical impedance spectroscopy is spectroscopy. You have to excite the sample in different frequency along the spectra, which can come from millihertz. Electrochemistry people use that to 1 megahertz, for example. Why you people stick in 1 meg? What's the problem with 10 meg? Electronic, I can tell you. Electronic goes up to 1 meg. Further on, above 1 meg is magic. Magic start to happen because 1 picofarad at 1 meg can destroy your signal. If you destroy your signal, that means destroy your modeling. Destroying your modeling, destroy your diagnosis. So you can give back to the patient the wrong diagnosis. 1 megahertz is, so you have to have to care about the system. You have to prepare, be sure that you are doing the right stuff. Going to 100 megahertz, wow, that's be super. Yeah, that would be a series that we can see in the Netflix. Yeah. Black Mirror. 1 megahertz is Black Mirror. But let's see what happens. We have to try. So if you don't try, someone else, might be a Chinese, will try. See? So bioimpedance analysis is more estimating the body fluid volume by measuring the resistance at high frequency, low amplitude alternating current. They usually use 1 frequency, 50 kilohertz, and they use from half ampere, No, I think it's wrong. I think this is not milli, is microampere, which is 0.5 milliampere. If you look at the standard IEC 661, you see that this will kill you. 1 milliampere can kill a man. Okay, 1 milliampere. That means depend on the potential as well. Okay, so that's the one of the impedance spectrum. A lot of spectra here. As you can see here, the interface, the interface is that straight line here, and that's the as you see, there's a peptide, a drop of blood, and a chamber here, and you are analyzing. So blood cells, you have, it's a cell, so you are expecting to have a dispersion in the electrical field and then reactance. And again, you can use 2 electrodes and 4 electrodes as we have discussed here before. I'm not going along that. So advantage is the technique: simple, quick, inexpensive, readily usage in population study, non-destructive tests. You can do as much as you want in biological materials. If you're using light, chemical stuff, or X-ray, you have to discharge the sample at any time you measure it. With impedance spectroscopy, you can measure as much as you want until the sample start to stink, of course. And then radiative free, label free. You can put in a people and leave and stay there for a long time. So that means you can wear the technology. The advantage is variability in the measurement. Sweat, one problem. Temperature is another problem. Pressure is another problem. For example, if we are building a probe and putting a probe on top of the tissue that we think that we have a skin cancer. Okay? And if you apply too much pressure on it, you are squeezing the water, ions of the water underneath the electrodes, then the opposition to the current flow will change. Therefore, the impedance change. If the impedance change, the modeling change, the diagnosis change as well. Because, not of the cancer, because you are so strong, putting a lot of pressure on it. So the pressure is a problem as well. So variability, and also depend. My heartbeat is 58 and rest. It's okay. The cardiologist said I have a athlete heart. Oh, can you believe that? Athlete's heart. They keep the heartbeat very low. Yeah, I'm okay. I don't have fatigue. I don't have my breath is okay. So it's usual for me. So the variability between one people to another may be different, and for electrical impedance spectroscopy is bad. And depends on the hydration level of the patient as well. So don't go to the clinic to do a bioimpedance analysis. You have to follow the protocol. You cannot run to the clinic to do the bioimpedance. You are in trouble. Okay? When you are going to measure your blood, what do you do? Feast. 80 hours at minimum. Okay? My diabetes, my blood glucose level is about 120 roughly at the feast, 80 hours. So that means I'm pre-diabetic. Okay, I'm in trouble. Right. So the theory is, as I said, we excite the tissue, excite the sample, and measure the response. You can excite applying voltage and measure the current. You can excite a sample using current, you measure the voltage. There's no way out. V divided by I, Z, impedance. Applying voltage, measure current. Apply current, measure voltage. Which one is the best? I prefer to apply current, by the way. So, applying voltage, you have a issue between the contact of electrode and the sample. Okay, there's a drop of voltage on it. And if applying voltage, you are losing voltage on that surface. Other than you applying current, you don't care about the interface. You don't care, just apply it, and the current will flow straight away and back to another electrode. Okay? Part of the energy will be in the sample stored, okay, as a capacitor. Other part will go away, heat resistance part. We need to use Lavoisier theorem, or Lavoisier saying that nothing in the world goes away like magic. Everything is converted to something. 1 grams of paper, if you burn, what happens? Disappear in the universe? No, it's converted to something. Ash and heat. Okay? Anyway, so we have to find a good model. We need a good model. Without model, we are back to the Stone Age. You have to have a good model. Because, can you show this graph to a cardiologist or some medical doctor? Oh, that's my output. What's that? So you have to build a model, and the model will give a parameters to the physician, to the medical doctor, and say, now I get you. So you have to convert this electronic information to a medical information. Well, and the modeling is impedance-based biosensor is, I can tell you, there's so many types of model over there. So many types of model. It's one of another model. That's what I'm saying. You have the binding stuff. You have the receptors here. That's the gold electrode. And that's the sample. You just put in a petri dish some sample. And there was some binding here. And then you can, this binding here will spread the electrical field. You are exciting the sample. Okay. And that's the good point. You can excite a biosensor without changing the binding process. So you are not stopping the binding process because you're exciting. As much as you keep the current in a very low amplitude. So the current density must be low. Okay. The current density depends on the size of the electrode. Ampere divided by the surface area of the electrode. Yeah? And you have your signal. And you have to fit this into this and extract this and use this parameter to give a diagnosis. For example, like this. I haven't done this. Okay? I just forgot where, I don't know why, because it's as you can see, you have a microfluidic device here, 2 electrodes, injecting current on one side and measuring the voltage here. As this cell, blood cell, whatever cell, just goes to this tunnel here, there's a change in the magnitude in respect to time, of course. This is not my simulation, by the way. The reference is here, but is behind this figure here. Sorry. Okay? This is not mine. But just to give you an example that what can be done. We can trap one cell, single cell, and measure the impedance. And also, it's possible to track the size of the cells and the structure of the cells. And we can count the cells. You know, cytology, people use impedance to count the cell. Is that right? It is right. But what about if you put AC current and do a bioimpedance analysis? We can actually say, is it a bacteria, fungus? How big is it? Is it, what type of cell is it? So it's kind of possible also extract more information if you have an impedance spectrum. And I don't know, I'm sure that you cannot read, but the references here, anyway. So we have been doing also these kind of electrodes here, 2 electrodes, 1 and 2 in the center here. 2 electrodes, for example, measuring cells, cell size, using different electrodes. We can do, like, as you said, you look like Elisa, yeah, you look like a squared petri dish with 1, 2, 3, and 4, 80 small walls. And we can print it out and put it. So we can expand it for 16, 32, 64. We demand time, we have to switch in that case, but it's possible. For example, we can easy to identify the impedance in ohms and with respect to frequency depending on the cell and the medium, and of course the size of the electrode. And this is one thing that we've been printing out, graphene. As you can see, graphene don't like water. It's afraid of water. It's hydrophobic. So it's a drop of water here, just staying like that, afraid of my graphene. But we've been measuring the conductivity and putting the MFIA, a impedance analyzer from Zurich Instrument. Zurich Instrument was sold and was bought by a German company. Have you seen? You know that? Roda? Yeah, they bought the company. And we've been playing, for example, see, dry, absolutely dry, nothing here. Real part, imaginary part. All positive. At least I'm in trouble. Yeah, because I've got a professor about the negative. Impedance here is not negative. The real part, imaginary part. Dry, absolutely dry. By the way, graphene is conductive. Not that conductance. Oh, not gold, not platinum. Graphene. So the amount of graphene in the polymer is not that much. But anyway, dry, and when you put a bit of water, just water, tap water, and you see the radius drop, the radius of, and when you take the water out of it, the electrode back to the normal, back to the black, when we dry this. What if we put some nasty stuff in the water? Let's put some peroxide of oxygen. Peroxide of oxygen. So the radius decrease, water, pure water, and water plus peroxide of oxygen. Very easy visually identify that something happens. Contains or not peroxide of oxygen, yes. But it's hard to say, what if I put another stuff? I may have the same decrease of the radius having another stuff. Yes, of course. Distinguishability between what you have inside of the water using bioimpedance is hard, difficult. How can you identify that you have fungus, bacteria, amoeba, or other stuff only using the spectrum of bioimpedance? It's difficult to say. Oops, really? Oh, that's it. And emerging of impedance meters, body composition, as I said, hydration, disease diagnosis, food quality, and healthcare. Well, now we are in future we are going to use everything in your body, and the electronic key, the system will take over, or Google will take over, yeah, Facebook and Microsoft will take over. No, that's explain why they've been charged in USA quite a lot. They want to extract data from you without your permission, yeah. Sometimes they release and note say, oh, Google, there was a lot of data which was how to say what I said that in English. There was a news saying that Google was not released. They capture some data from Google, yeah, without your permission, and Google system was unable to stop. So it's a problem, okay? Because anytime you switch the camera a few seconds before they are recording, if I'm going to talk about here shoes, in a couple of minutes I'm going to receive a news about shoes. Say, what? They are listening me. Yes, they are. A bit. Okay? So we are using now everything, tools, news, and electronic. Now people are using flexible electronic. You put everything, bandage. People have, and for glasses, you know, Google Glass now. And all the electrode, you can have all the sensors in a t-shirt using textile electrode. You just put the t-shirts on, and your vital signals are measured, sent by area RF some point. Okay, and well, we need energy. Well, let's produce our energy. Let's take the energy from the sun. Let's take the energy from your step. You are moving up and down and up and down, and you are storing energy in a capacitor, in a battery, stuff like that. So that's the future. Personalized nutrition and fitness plan. I think we have to improve the body composition diagnosis. Okay, early disease detection and prevention. As he said, Professor André said about one example. Prevention, stopping millions and millions of people suffering. Another thing that we have been discussing, me and Martin Keith Cox from the company in Alaska said, people who have been doing dialysis, is one point is that how can you decide when is the right time to back to do the dialysis? So a system that you can wear and measure your bloodstream, your edema, and decide if you need to go back to dialysis more time or not. So and I've been working in a glucose watch like that shirt, e-glucose, measuring the blood glucose without blood. Explain that to people is kind of very hard, but I'm not using only bioimpedance. Okay. And you can buy devices in the market, portable ones, wearable ones, smartphone based one. That's a huge amount of devices. Solatron is a United Kingdom company. I don't know if they are selling anymore, but HP helmet package, I think it's kind of old. Ageland as well, they sell now. They all the companies called Zurich Instrument now is a company. Science Spec is also a company in Germany that now they are selling platforms, electrical impedance tomographic platforms. Is a machine for doing tomography, electrical impedance tomography for research on labs. And believe me, up to 94 channels. 94. I'm buying one 32 channel. It's expensive, but that's the money we have. But you can build your one. Okay, you can build your one. You can build one by a development kit called AD5940. is impedance analyzer. You can buy it. AD5940. Okay, again, count, write down. So that's, you can buy your one, and you need a excitation, a measuring system, a gain phase detector in order to retrieve modules and phase. That's it. Convert to digital, and that's it. And converting that to digital, any Arduino can play and can ask for a SP32 from Adafruit. They have a Bluetooth, and they can do it. At the end of the day, that's what I want. One chip, an ASIC, to perform all the data, containing the oscillator, the measuring system, the electronic stuff, and set for an impedance analyzer to be used for any application, not only food, health, but the challenge and limitation: accuracy and reliability issues. Accuracy is an issue. As you go further high to the frequency, we have accuracy problem. User error and variability, so people need to know exactly how to operate it, because I can give the device to a people, to some research, to a student, to perform that measurement. Next day, other one will do, probably there will be variability problems because of the method of measuring it. The distance between the electrodes will change the stuff because of transfer impedance, as he said, the change. So that's why also I have been spoken with Marin that that's one thing that people have not been using is publish resistivity upon frequency, not resistance or reactance, but the resistivity. So that resistivity does not depend on the size of the electrode, does not depend on the distance between the electrodes, doesn't care if you're using gold, platinum, your electrodes round, squared, resistivity. And then resistivity can be compared to everywhere. A paper published in China, published in Brazil, published in German, published in Italy, is resistivity one to another. And that we have this ethical consideration. Be careful doing in vivo. You need ethics committee. You cannot publish a paper without ethics committee. I've been rejecting papers just because there's no ethical committee on the paper. 10 patients, 15 patients, and I say, oh, with no committee, go away. Okay, we have to respect this. There's a standard, IEC 661-1, -1, -2, -3, well, depend on the technique. Real-time label-free detection and analysis, challenging. People move. I'm using one sensor here, and I'm moving my arms, and the movement artifact will play a big hole in it. Electronically speaking, is a nightmare. So real-time, that means demands a lot of energy, lot of switching, a lot of memory, so on. Non-destructive analysis, this is important. That means we have to keep measuring without using more electrodes or more sample. Minimal sample preparation, so you don't need a liter of blood. Just 1 ml, 1 milliliter is enough. So the smaller amount of sample, the better. Okay, but the smaller the sample, the smaller is the electrode. The smaller is the electrode, the bigger is the impedance. The bigger is the impedance of the electrode, the trouble is in the shoulder of the electronic engineer. Okay, so that's a good thing. regulatory, well, I'm going to move that. I'm just showing some potential impact in the healthcare industry over the last. It is a diagnosis for 2030, okay? And the potential impact of healthcare is quite huge from now to 2030. Well, development of sensitive and selective biosensor is a problem. We can select. Well, why not? As Professor André gave a talk in the first day here about why not do a selection that we can analyze a lot of things in one sample, having, for example, multi-selective biosensor. Okay, not. You can select one for Zika, one for dengue, one for this, one for this, one for that. So why not? Can't you not do using at once and analyze a lot of microorganisms at once? Integration of a biosensor. So miniaturization is important. That means charge, battery. We are in problem with battery. We cannot use this holding the battery on your back. You give you a head bag, backache. So miniaturization, standardization and validation for biosensing platform. Validation is quite difficult. We have to do a study, medical study, and we need, at the end of the day, we need to convince medical doctors to use your technology, and that's a hard job to do. Hard job, you know. I think it's easier for biologists to convince biologists to use the technology. I have a biologist here, but medical doctors is difficult, because at the end of the day, the medical doctor will trust in his or her knowledge, not the device itself, because the one who goes to jail is not the device, it's the doctor, medical doctor. So let's move a bit here. So a lot of conclusions given by this talk. We need to, I'd like to move up to the end because we are running out of time. Thanks for attending. This is being sponsored by the federal, the state agency, funding state agency called FAPESC. The first coffee was paid by MINIPA. It's a voltmeter company selling device for laboratory for undergraduate students, like for not for research. They have some nice voltmeter. 6.5 digits. So, and this is the old logo of the company run by Martin Keith, who also kindly paying a part of the coffee breaks. And the University of Oslo, I'd like to thank as well, because is paying the EasyShare. EasyShare is the system that used to send a paper and do the reviews. Now EasyShare you have to pay. A long time ago was not necessary. And I would like you to call for papers, please. October there will be the 5th Latin American Conference on Bioimpedance. That will be in Florianopolis, island, 52 beaches around, nice, but not in October. It's freezing water, I'm afraid. That's my contact for bioimpedance for this conference. I'm running the conference, not in Joinville. Okay, the submission system is open. EasyShare. And also this, I'm going to finish here. I'm going to leave with you in Mexico City, in Monterrey, in Mexico. We are going to have the International Conference on Electrical Bioimpedance and Electrical Impedance Tomography. Altogether, 2 events in once. That will be in June 2025. Thank you very much. Sorry for the delay.
We thank Professor Pedro for the presentation, and we open for any questions from the audience.
Thank you so much, Professor Pedro. It was a fantastic talk. I'm curious about the use of these machine learning techniques to improve a bit the selectivity using bioimpedance. If you can talk a bit about this topic.
Yes, we have been measuring a lot of cow milk. Yes, some local farmers. Milk is a very dramatic, complicated, complex substance to analyze because it contains fat, proteins, solid substance, a lot of stuff. And we try to use network analyzer, not network analyzer, neural network. Didn't work. Okay, the data was confusing, measuring impedance, modulus, and phase. And I think using machine learning technique, but not only using bioimpedance spectra, but also measuring light spectra, at least 3 infrared, 1 red, and measuring the temperature of the milk. It's important because the impedance increased 1.7 milliohms per degree Celsius, at least for saline solution. Perhaps in milk is less, but increase. And also measuring the pH of the milk. And put all this information to a machine learning, say, decide. Okay, but you have to do the gold standard. And the gold standard is flux cytometry. They count cells and they will count how many somatic cells they have. And this will be your gold standard, of course. And you can train the network. And I think it's feasible because, I'm saying that because we are running a machine learning technique, use machine learning technique for measuring the glucose of your blood. Impedance spectra, modulus and phase, 3 infrared, 1 red, the temperature of your body, the skin, also the body, and the humidity as well. So all together, giving to the machine learning an artificial intelligent algorithm to do the rest. Of course, into comparison to a standard, which is the one you remove the plasma from the blood and give the plasma to the photospectrometer to get the glucose. That is standard, worldwide standard. It's possible. I think that's the future. There's no way. Only bioimpedance itself is kind of small application for certain material analysis, not complex ones.
Thank you.
Thank you, Pedro. We were talking about measuring honey. Honey earlier.
Honey sweet.
Honey sweet.
Yeah.
Yes. And then you were talking about the biosensors.
Yeah.
And putting antibodies in, and then you would have antigens that attach to the antibodies, right?
Yeah. Yeah.
And then really what is the difference between measuring, say, sugar and honey compared to measuring antibodies and antigens, because neither one would have an imaginary value, correct?
Yes, but you ask me now, you answer me now. What can you add a marker in the honey bee honey, yeah, and a syrup made by corn, can you add something into the sample in order to, like a marker, in order to react and give you something back in order to the biosensor to attach on it? So for example, what I'm saying is that you put a drop of honey in something marker and you mix it up and put in your biosensor, and if there's a bind, honey, if no bind, no honey, no bee honey, it's syrup. So it can be that you need something to recognize, to do the binding or to transform, given another product. In that case, the binding happens, and then you can detect by using spectroscopy.
But there still would not be any reactants in an antibody antigen
Well,
combination.
depend on what kind of biorecognition system you are using. Yeah, but I don't know. It's a bit of more electrochemical analysis. So electrochemical analysis, that means very, very, very low frequency, which comes to millihertz up to 10 kilohertz maximum. So actually what you see is the interface, more resistance. So actually you don't need the other part of the spectra. But if you're looking some bacteria growing inside of it, but you are not interested to say if it's bee honey or corn honey, and if you are looking at bacteria inside your bee honey, and you can test without bacteria and with bacteria, that you can compare, and that will be a spectra. Good.
Yes.
Okay.
We'll talk more. I have more questions about it.
Okay. Any more? Okay.
Thank you. Nice presentation. In one of your last slides, you were talking about regulatory laws. I don't know.
My last one.
Maybe
That one? No.
Previous,
Sorry.
previous
Sorry.
one, previous. Yeah,
This one?
regulatory. Yeah, regulations. Yes, because you said that this bioimpedance analysis depends on the electrodes and the distance of the electrodes, materials, and the movement of the patients. In, for example, mechanical engineering, we have the standards for tests. Is there such a thing for bioimpedance?
Yes. Yes. It's actually IEC 6061. IEC 6061-1 give you all the safe standard for electronic device, including electrical impedance analyzer. And by the way, the electrical impedance tomography is also impedance, but not using for diagnosis in a sense that you have to have a model, but they transform that in an image algorithm, give you pixels of your lung. It was done using the 6061. Okay, and of course you have to use some other standard like ISO, because you have some movement part, for example the belt on it, you have to use the ISO one. When you have a mixture between electronic, for example an ultrasound that move the big magnet around you to give a 3D, you have to stick with the IEC and ISO, because you have mechanical parts on it as well. So it's kind of hard. But yes, we have a standard for bioimpedance meter.
So your watch is
Yeah,
following
let's
this?
see. Let's see. We are talking about one consultor in Anvisa, okay, about it. And my watch is considered to be C2. By the way, C1 and C2, that means Anvisa I don't need to do um, permission to use the device. C2 is safe, is battery, so I don't have to do extra exams on it because it's safe. It's class 2. There's a class 2, C for class. Class 1, class 2, I think is in FDA is the same. Yeah. Okay.
One last question.
Yeah.
In this direction, I'm just wondering if
Yeah.
the aim would not to sell these things for the public, but to other researchers, because that's what the company is doing with the tomography.
Yeah.
Right? It's not selling to doctors right now, it's selling to researchers, right?
The tomography, no. They are selling to hospital. The tomography is sold by Team Pell. Okay. They have some part of the company. There's a company which is in the market. Okay. You can buy part of the company. Philips has some part of the company, and they are selling actually to hospital for a small price. I know, just to show how good is the, and they've been doing quite a good job, especially because we had the COVID-19. A lot of people in a respirator, and you see the lungs going up and down, the dynamic up and down. That means breath out, in and out, and you can see right away which lung is breathing good and other one is not. Someone arrived in the hospital with a motor accident. I'm saying motor because 90% who needs in a crash is motor in Brazil. Okay, 9 of 10, and the doctor don't know what's inside. Everything is broken. Sometimes 2 ribs perforate the lungs, and what is inside? I don't know. Let's take this guy to the MRI. Wow, MRI is in 2nd floor, but I cannot take him there because he's not breathing. So I have to put his direct to the respirator, and you need to do the exam there. So what they do, X-ray, dynamic X-ray, again, come here like that, and do some shot in time, and you have a kind of a idea. But what's inside? They have to do that tracheostomy sometimes and ventilate the right or the left one straight away, because the left one is not working. I can see in the image. Only this is working. And the apse and the bottom of cannot work, so it's meshing. So I need to move the patient from one side to another because one side of the lung is not. So see how good is the imaging device in the intensive care unit, running real time all the time. So I think we've done with the questions, because the coffee is cold. Sorry. Yep. Please. No more question. No more question. Yes.
You said that you would like to measure resistivity.
Yeah.
You want to measure the material property because that will make it easier to compare between research groups. But is it realistic? Can you calculate resistivity from different electrode systems and geometries and things like that?
Realistic in what a sense? I mean,
No, I would claim that it's in most cases it's impossible to calculate the resistivity based on impedance measurements, because you don't have full control over the geometry.
yes, that's a good point. You have to have control of the geometry. What if we model using comms or multiphysics the geometry, because in order to transform resistivity Z is equal to K probe factor times resistivity. Is that right? That's the one. K factor is a geometry. The unit is meters or millimeters times the power of -1 times resistivity, which is ohms meter. So meter cutoff meter, you have ohms. But the problem is the probe factor. The probe factor depends on the size of the electrode and the distance between the electrodes. But what if we do finite element analysis? We can do finite element analysis and find out the probe factor, and then we can use a probe factor to convert impedance to resistivity. Is that possible? You're not sure. I have seen people doing that in Sheffield, doing infinite analysis, finite element analysis, looking for the probe factor. And you can compare if your probe factor modeling is good or not using standard solution that you know for sure the conductivity. And then we can say you can compare simulation. Thank you. Other question? People, it's very important now. Please give your name in the registration desk in front if you want to go tonight at 8 o'clock in a pizzeria, Rodizio, okay, with pasta, pizza. We start at 8 o'clock there, we meet 8 o'clock. I need to phone the lady in the pizzeria to say how many people. She's going to prepare a table for us. 79 reais, roughly $15 roughly, okay, for each one. So please give your name. If you don't want, don't give your name. That means I know that you don't want to go. Thank you very much.